Okay, so welcome to the last lecture. So yesterday, we started talking about this question of strong and weak learning. So we had already talked about strong learning quite a lot. That's just our regular notion of pack learning. And then we started talking about this notion of weak learning, where rather than requiring that the learning algorithm get arbitrarily low error rate, as small as we want, it's only required to get error a little bit better than random guessing. Again, if you guess randomly, you'll be right half the time. So in weak learning, you just have to be a little bit better than random guessing. The learning algorithm only has to be a little bit better. And then I left you with this exciting cliffhanger of whether these two notions are equivalent, or if it's the case that there are some things that can be weakly learned but not strongly learned. In fact, the answer turns out to be that these actually are equivalent, that strong and weak learnability are the same. So you can say that in formal mathematical terms. So we already defined what strong learning is. It's really just our notion of pack learning. And I won't go through it, but you could imagine how you could change that definition so that rather than requiring this for all epsilon, we're requiring this for any gamma, for just some. There just has to exist a gamma for which that's true. So it's actually a theorem that these two notions are equivalent. So in other words, a class C is strongly learnable if and only if it's weakly learnable. So what I want to talk about today is how to show that that's true. So to show that that's true, what we need to do is we need to come up with a method that will take an algorithm that weakly learns a class and convert it into an algorithm that strongly learns that same class. That's the technique we're going to use. And it's worth, before we get into that, maybe it's worth talking a little bit about what this means. What it means is that when we're talking about pack learning, this shows that learning is an all or nothing phenomenon. Either you can learn a concept class all the way in the sense of being able to get arbitrarily high accuracy, or if that's not possible, it means it's not even weakly learnable, that you can't even learn a little bit better than what you would get with random guessing. So either you can learn it all the way, or you can't even learn it a little bit beyond the trivial amount. And also, the fact that these are equivalent suggests that there might be a practical algorithm lurking inside there, because to show weak learning implies strong learning, like I said, we'll have to come up with a method that will take a really crummy, mediocre algorithm and convert it into one that's very, very highly accurate. So there's a potential for actually coming up with something practical. Okay? So let's see how to do that. So what we're given, so we're imagining that we're given access to a weak learning algorithm like this one. Okay, so we're given a weak learning algorithm A that can take any examples from any distribution and produce a hypothesis that satisfies this criterion. Now there's also the part about with probability at least 1 minus delta. We're mostly going to ignore that. Okay, so we're given a weak learning algorithm A that has this property. And the second thing we're given, of course, is data. So our examples x1, y1 through xm, ym. And they're coming from some distribution. We'll be talking about several distributions. So let me use script D for the true distribution that's generating all the data. And what we want what we want is to find a hypothesis. I'll use capital H for the hypothesis, whose error is small. Okay, arbitrarily small. Okay, arbitrarily small meaning at most epsilon for any epsilon, provided we're given enough data. Okay, so this is what we want to do. So this is a weak learning algorithm, so it's like a black box or a subroutine that we can call whenever we want to, we being the algorithm that's doing this. So an algorithm that is able to do this, that can take access to a learning algorithm and data and come up with an arbitrarily small, an hypothesis with arbitrarily small error, an algorithm that can do that is called a boosting algorithm. Okay, so the term boosting has come to mean something beyond that. It's come to have a broader meaning than that in terms of how it's used, especially in practical settings. But its actual, real, original, mathematical, technical definition is an algorithm that has this mathematical property, that when you give it access to a weak learning algorithm, it can find an epsilon good hypothesis, a strong hypothesis. Okay, yeah?
For the weak learnability, so this is a gamma existence, right? So, but for the strong learnability, we have like for any epsilon, we can find this. So when you have any like existence gamma, so you probably have like a subset of your hypothesis class that actually is doing better than random, and then you can find gamma. So my point is like, are you doing like a minimum gamma, or like what is?
We're just saying we're given an algorithm A, and it has the property that there exists gamma, such that for all distributions D, if you give examples from that distribution, you'll get this error rate. So, yeah, so you have an algorithm that gives you hypotheses with 48% error rate, no matter what distribution you do, okay? So, yeah. Okay, so how are we going to do this? Well, all we have to work with is this learning algorithm. I mean, the data too, but otherwise all we have to work with is this learning algorithm. So a natural thing to do, which I think was actually suggested yesterday, is to take this learning algorithm and run it multiple times on our data. So we have our learning algorithm A. I'll draw things a little bit schematically. And we're trying to create a boosting algorithm around A. So this is our little subroutine, our black box, and this is our boosting algorithm. And the input to the boosting algorithm are examples from this distribution script D. And a natural thing to do is to run this algorithm multiple times. So we run it once, we get a hypothesis H1, we do it again, get a second hypothesis, and maybe we'll do that capital T times. Okay, we haven't said how we're going to run it, but somehow run it a bunch of times, get a bunch of hypotheses, weak hypotheses, and then somehow combine them into a combined hypothesis that gets output here. So that's the basic idea, very simple idea. As I go through this, I'll also write pseudocode over here for the algorithm. So the pseudocode of what I'm saying is that we'll run this algorithm in rounds, and on each round, we'll run this weak learning algorithm, and I'm leaving a space here, to get a hypothesis, a weak hypothesis, HT, and as usual, it's a weak hypothesis that just maps instances to the labels, and I forgot to mention that we'll continue using labels that are -1 + 1. Okay? Okay. And at the end of the day, we're going to output H. Okay. All right, so, well, that's fine, but what are we going to run this algorithm on? So a natural idea is we could just take this weak learning algorithm and run it on the data we have already. Just run it multiple times on the same data set over and over again. So if we do that, what's going to happen?
If the algorithm is doing it, it will give the same.
Yeah, it's entirely possible and reasonable that this algorithm will just output the same weak hypothesis over and over again. And then we're not getting anywhere, right? We're just getting the same weak hypothesis over and over again. It doesn't matter what you do with it. Nothing's going to happen. So somehow there's an intuition that we want to force this weak learning algorithm, we want to force it to do some work. We want to force it to pay attention to the hard examples that it keeps misclassifying. Okay? And the only thing we have to work with this weak learning algorithm is the distribution of examples that we feed to it. So somehow we want to be feeding different distributions to this weak learning algorithm on each one of these rounds. Okay, and being schematic, really means random examples according to that distribution, but I'm just being schematic here. And we have to figure out a way of coming up with these distributions so it's focusing on the hard examples. So what we do over here is we're going to run this algorithm A on a different distribution T, dt, on every round. Okay? Yeah.
So you said the only thing we have for our data set is the distribution from which it's drawn. I think in most of your other, or I think in all of your other lectures, you said that the order of the data doesn't matter. We just kind of give it to it. But I was thinking about Seb's lectures about convex optimization, like stochastic gradient descent. The order of the inputs does matter.
Mm-hmm.
In fact, that's kind of the whole. You can permute the inputs and arrive at a different proposed minimum, and then the sort of the minimum of all those outputs is kind of the best answer. Fine. Is nothing is that sort of framework different from this one somehow?
Well, okay. So A is just a black box. So we just give it a batch of examples, and we're kind of assuming.
They seem to always be insensitive to the order of the data.
Yeah,
Okay.
it's not really important to what I'm going to say. I mean, it is definitely important that the data is IID, so all orders are equally likely. But okay, but we're just viewing it as a batch. The algorithm is just given a batch. Okay, so let's see. So we're going to run this algorithm multiple times. Now, each time we get a weak hypothesis, HT, we can measure its error as usual. So it's error of HT with respect to the distribution on which it was trained. And we're assuming that that is going to be at most, well, actually, let me not write it that way. First of all, let me do a little notation and call this epsilon t. And we'll also sometimes write it as 1/2 minus gamma t. Okay, so gamma t is just how much better than random guessing it's doing. And our weak learning assumption from over there is that the gamma t's are always at least some number gamma. Okay. All right. So fine. So we keep putting off the hard part. The hard part is figuring out how to do these distributions, how to compute these distributions. And like I said, the boosting algorithm wants to choose these distributions so that we're focusing on the hard examples. Now, of course, in principle, an algorithm like this is supposed to be able to work with any distribution over the space of examples, but the boosting algorithm only has this finite batch of examples to work with, so we're going to focus just on distributions over this set of examples that are given to us. Yes, question?
Guarantee for like probability is on the expected error, right?
It's actually with high probability, like with probability at least 1 minus delta, this will happen. But I just want to gloss over that.
Well, or like the error on the true distribution, like the generalization error, or is it the training error?
It's on whatever okay, this is a good question. It's on whatever distribution we use to generate the examples. So as the boosting algorithm, which is constructing these distributions, the boosting algorithm can decide that, oh, the real distribution, as far as this algorithm knows, is a distribution that just gives weights to the examples that appear in the training set. Okay? And so as far as this algorithm knows, that's the real distribution that it's working with. And so its guarantee has to be with respect to that same distribution. Okay? Yeah.
We talked about some examples in past classes, like predicting the weather or something, where like clearly even with arbitrary data, you're not going to do arbitrarily well. I guess why are the assumptions here different than the assumptions there?
So you're saying this should not be possible? Because if you're trying to predict the weather, you can never get nearly perfect.
There must be some assumption that's different here than there.
Yeah.
I'm not saying that
Yeah.
it is.
So if I'm understanding your question, when you're talking about something like,
It's like heads 48% of the time.
yeah, so the weather you can predict pretty good, but you can't predict perfectly. So why doesn't that violate this? The reason is because the weather, in the case of the weather, we only care about one distribution. In this notion of learnability that we're talking about, both of these, the algorithm has to be successful for all distributions. That's the difference. Yeah, good. Yeah?
But here we're also assuming the y is a function of x, right? Like there's a function
Not
c.
directly, but effectively. That it doesn't seem like that, right? It's not in the assumptions, but since ultimately we're going to get nearly perfect accuracy, that almost falls out from that. Yeah, but we're not explicitly assuming that. Yeah.
So to make clear, you're saying that the weak and strong learnability, it is for every distribution this holds in each case.
Yes. There exists gamma such that for every distribution. Yep. Yep.
So just to clarify on his question, so this would not apply for a situation where x is kind of a function of y, like a mixture model.
Where x is a function of y.
Well, like if you think of a mixture model, right, you have like
Yeah. No,
maybe
don't
two-
think about mixture models. Yeah. let's stick to classification.
Okay.
You've given the
Well, if you want to classify like which,
yeah.
like if you think about maybe two normal clouds that overlap a little bit.
Don't think about that stuff. I'm sorry. Yeah.
So maybe you're going to get in here, but I guess I'm unclear on what C is now, like the class C.
Yeah, so we're actually not assuming there's a C explicitly. Okay, so we're not explicitly, okay. For this theorem, yes, the labels Y have to come from some concept. Okay, but for what I'm doing over here for deriving this algorithm, we don't actually need that assumption. Yeah, good, clear. Okay, yeah.
So, just in terms of delta, the certainty that the weak learner will work at each step.
Yeah.
Here you're asking that it work properly at all.
Yeah.
steps.
Can we
Is
just
that a problem?
can we just do that? Because that just work with me. Okay. Okay. Where was I? Yes, we're trying to construct these distributions dt. Okay, so a distribution dt will always be over these examples. So I could write it as dt xi yi for the distribution on the ith example, but that's going to get really tedious. So I'm just going to abbreviate this as dt of I. Okay, so each of these distributions, I'm going to write it as if it's a distribution over the indices of these examples, but really it just represents a distribution over the examples themselves. So what we need to do, or what the boosting algorithm needs to do, is choose a distribution on every round. So on the first round, don't have any information. So the most natural thing to do is just to use uniform distribution over the m examples. Okay, so our first distribution will just be uniform. And now what do we do on each of these rounds? Well, the booster used DT, or constructed DT, and used the weak learner to find this weak hypothesis HT. And now we need to construct the new distribution DT plus 1. So what we do is something really simple. What we do is we take the old weight on this particular example, I, so the ith example in this training set, and we multiply it by a number. So if the example was correctly classified, if it was correctly classified, so the prediction of HT, the last weak hypothesis, matches the correct label, then we want to decrease its weight because we want the weak learner to focus next time less on that example because it seems a little easier because we got it right last time. So we multiply it by a number which is less than 1, and you could write this number all kinds of ways, but the math is going to be nice if we write it as e to the minus alpha t. Okay, where alpha t, I'll say what alpha t is in a minute, but it's positive. Okay, sorry I didn't leave room. Okay, otherwise, if the example was incorrectly classified, if we made a mistake, then we'll multiply by e to the positive alpha t, which is bigger than 1, so we'll increase its weight. Okay, so we're just trying to focus our attention on the hard examples. And the reason to write it this way, or one reason to write it this way, is we can just write this more succinctly as e to the minus alpha t yi ht of xi, because they're plus 1 minus 1, so we can just write this update in this form. Now, of course, when we do this, when we do all this multiplying, we'll no longer have a distribution over the m examples, so we need to normalize. So zt is normalization. Okay? And I didn't say what alpha t is, so let me fill that in, and don't ask me why I picked this, but later you'll see. I'm sorry. Okay, dt, it's log 1 minus epsilon t over epsilon t. Why did you pick that? I'm not telling. I'll take, but I'll show you later. Okay? Right, so that's how the distributions get updated. And then the last step is we have to take these and combine them into this combined hypothesis. Okay, so this combined or final hypothesis H takes a new example X, and what it has to work with are all of these weak hypotheses that we've collected, H1 through H big T. So each one of those weak hypotheses is giving its own prediction on this new test example of whether it's a positive or negative example. They're all predicting plus 1 minus 1. And H needs to come up with its own prediction. A natural thing to do would be just to take majority vote of those weak hypothesis predictions. We're actually going to do something a little bit different. We're going to take a weighted majority vote, where the weights will turn out to be these alpha t's again. And to write a weighted majority vote, one way to do that is to just add up these numbers. Again, these predictions are plus 1 minus 1. And then if this weighted sum of the predictions is positive, then we predict plus 1. Otherwise, we predict minus 1. So I'll write sign SIGN, this SIGN sign function is just giving +1, -1, or it could also give 0 for a prediction. Okay, yeah.
So can you explain why it's not important that the original distribution script D is over maybe a continuous space, the space of features X, whereas this distribution...
Why? Yeah, so there are some boosting algorithms that do work directly with the distribution. And so, yeah, so why should this generalize is basically the question. So we'll hold on to that. We're gonna. I don't think we'll be able to do a full analysis, but I'm gonna try to give the main ideas of an analysis. Okay. Yes. Actually, is the projector coming on? It doesn't. I'm not seeing the button for hide on hide. Did it? Help. Help. Or maybe they can control it back there. Okay. Sorry, what was the question while they're...
Ask what determines capital T, or you could tend to...
yeah. Okay, we'll come to that. Good, yeah. Is this thing warming up? Okay, wait, he's waving to me? Yeah, right. So M has to be large enough. Yeah. So
Do we know what's the lower bound of M that you have?
we're gonna do an analysis and try to come up with the answers to that. Yeah. So this is why theory is awesome, because we can answer questions like that. Yeah. Oh, did it do something? Darn, it was working before. Okay. So let's do a quick example. Okay. So in this little example, just a tiny toy example. So there are 10 training examples in the square, 5 positive, 5 negative. And the weak hypotheses, I wrote classifiers, but classifiers same as a hypothesis. So the weak hypotheses will be vertical or horizontal half planes, as you'll see. Okay, so on the first round, the distribution is uniform over these 10 examples. So the boosting algorithm gives this data, this weighted data, to the weak learner. And the weak learner chooses a weak hypothesis, like this one, that classifies everything to the left of that line positive, everything to the right as negative. So it classifies 7 of the examples correctly, but it misclassifies those 3 that I circled. So epsilon 1 is 30%, alpha 1 works out to be 0.42 about. So on the second round, what we do is we increase the weight of those 3 examples that were misclassified and cut the weight of the other examples. And again, we pass this to the weak learning algorithm that maybe chooses this weak hypothesis. And so it misclassifies those 3 examples there. And so on the third round, we increase the weight of those 3 examples. And you can kind of see what's going on here, that you have these 2 examples here and these 2 examples here. They have really low weight because they were correctly classified on the last 2 rounds. So we care about them less in this distribution. And so when you pass it off to the weak learning algorithm, it picks a weak hypothesis like that one. And yeah, so now we have these 3 weak hypotheses. So here T equals 3. Each one of these misclassified 3 of the 10 examples. So it had a fairly high error rate. And for the final or the combined hypothesis, what we do is we take H1, H2, H3, those 3 weak hypotheses. We weight them by the alphas. Maybe it's better to point over here. We weight them by the alphas and take the sign, and you end up with a more complicated function like this one, which correctly classifies all 10 examples. So that's it. Proof by example. We're done. Right? No. Okay. Okay, so, right, so it's a contrived example, of course. Yeah?
What if you know exactly what the scripted P is, or you have a highly unbalanced class? Do you have to construct the D1 differently, or you can still use
Okay, if you know D exactly? I don't know, yeah, well, you could always pretend you don't know it, and then do the same thing. Yeah, let me put off these more discussion questions like the balanced. I mean, it's a very good question. If the data set is highly imbalanced, what do you do? But let me just put that off a little bit. Okay, so yeah, these methods don't work as well, but the theory doesn't really matter so much. I mean, one thing that you can see that's going to happen if the data set is very highly unbiased, unbalanced, is that it could, on the very first round, choose a hypothesis that says all examples are negative. And if you go through the math, what will happen is on the second round, it will give exactly equal weight to both classes. So it kind of automatically does this balancing things to make things as hard as possible. Yeah.
When you say run A on B, does it mean the entire data set? I mean, you have some,
Yeah.
you're running it on all of them.
Well, okay, so you could do it two ways. Yeah, so what does it mean to run on the data on DT? It could mean draw examples randomly from this distribution, which is just, so basically resampling according to that distribution on the data set. Or some learning algorithms can take these weights directly. Sometimes you can just use these weights.
So it's not like you ran on the entire data set as we did in this example.
In this example, I ran on the entire data set using the weights. So I designed a weak learning algorithm that uses the weights directly, but minimizes the same thing. Still minimizes this. Okay? Yeah?
How do you determine the number of t-steps that you need to...
Yeah, let me come to that. Okay, is it okay if I keep going? Because I only have this hour. And I love the questions, I really do. But if you could just hold on to them just a little bit so I can get to talk about some of these things. I mean, of course, if something's really unclear, then please do ask. But okay, so this was a contrived example, clearly, to illustrate the algorithm. But the first question we might ask is, does this algorithm always drive down the training error quickly? Does it always drive down the training error quickly? And the answer turns out to be yes, that it always does. Always does, given this weak learning assumption, given the assumption that the gamma t's are all at least gamma. That's going to be the assumption we always work with. So here is the actual theorem that we can prove. Wrong slide. Okay, here's the actual theorem we can prove. Okay, so here is the training error of the combined classifier. And the claim is that this is at most the product over these t rounds of this function in terms of the epsilon t's. Okay, so that function, well, it's a little bit hard to interpret, that function. But remember that we can write epsilon t in this equivalent form as a half minus gamma t. So if you write it in that form, then equivalently it's equal to this, product of square root 1 minus 4 gamma t squared. So you already can see that that number in the square root is a little bit smaller than 1. So if you take the product, it goes down very quickly. Or we could use our bound on the exponentials, 1 plus x at most e to the x. And if you do that, then this is at most e to the minus 2 times the sum of the gamma t squared. Okay? So if we have this weak learning assumption that all the gamma t's are at least some positive number gamma, then this bound says that the training error is at most e to the minus 2 gamma squared times capital T. So this is saying that as long as gamma is positive, any positive number, the training error goes down exponentially fast. So it's always going down quickly as long as we have that weak learning assumption. And by the way, this theorem includes all the assumptions that are required, which is none. This theorem always holds. Okay, so it's always true. For any data set, you don't need randomness, you don't need anything. Okay? Except here. Except we assumed gamma t, at least gamma. Okay, so let me sketch the ideas of this proof. Okay, so the first step, which I won't go through, but we can just take, this gives us a recurrence for dt plus 1 in terms of dt. And we can just take that and unravel that recurrence. And if you do that, what you find is you can just write down an expression for the final distribution. So the last distribution after capital T rounds, because of the way I index things, will be dt plus 1. That's the final distribution. And you can just write it as e to the minus yi times f, where this f is exactly the expression that appears here. Okay? And then on the bottom, you get m, which comes from the initial distribution, and the product of the zt's, because you're just multiplying it out. So I put a proof on here, but it's really just very straightforward, just using this recurrence that we started with. Okay? That's step 1, and I'll post these. Okay, that's step 1. Okay, step 2 is to show that the training error is at most the product of the zt's. So these zt's, again, these are just normalization factors. Maybe they just seemed like an afterthought, like, oh yeah, we have to normalize at the end. But actually, it turns out that the training error is upper bounded by the product of those zt's. So they actually play a really important role. So to prove this, we can, I said already that the combined hypothesis H is just the sign of this F, which means that H makes a mistake if and only if Y and F differ in sign, which is if and only if they're not positive. We've seen this type of thing multiple times already. Okay, so the training error, we can just write it down. That's our training error. And we can rewrite the training error using this observation at the top, that a mistake means Y times F is not positive. And then we can take this indicator variable, and we can do this really ridiculous upper bound. We can upper bound it by an exponential. And you can check that this is true because if Y times F is actually not positive, then this exponent will be not negative. So when you do the exponential, you get at least 1, which is at least the indicator variable. An exponential is always at least 0. So you can check the two cases. And then we can go back to step 1. Remember step 1, we had exactly that same exponential appearing for our expression of dt plus 1. So we can go back and take exactly this exponential that we saw in step 1 and plug it in. And we get an expression like this. The m's cancel out, and we get the sum of the distribution, which is just 1 because it's a distribution, and all we're left with are the product of the zt's. So the training error is at most the product of the zt's. All that's left to do is to compute the zt's. So to do that, well, zt is just this normalization factor. So to compute it, you just add up these numerators. So that's what I've done up there. We can take these and break them up. Actually, all I'm doing is I'm actually using this expression really for the dt's. And when you do that, yeah, so that's really just rewriting the zt using that first expression. And then this first term, I hate this walking back and forth. Okay, this first term, if you think about it, is just the sum of the weights of the misclassified examples, which is really just exactly our definition of epsilon t. And this one is the correct examples, and it's just 1 minus epsilon t. These other parts act as constants. So when you simplify, you get an expression like this. So now we have an upper bound on the training error in terms of epsilon t and the alpha t's. We want it to be small, so we can just minimize over alpha t. We get to choose alpha t however we want to. So we'll just minimize it using calculus, and you get this choice of alpha t, and when you plug in, you get that. Okay?
That's how you get the alpha t's.
Sorry?
That's how you get the alpha t's.
That's how we choose the alpha. See, didn't I promise? I keep my promises. Okay. Okay. Sorry, I didn't mean to scare you with questions. All right. Okay. Okay, great. Training error. Wow, we can make the training error small. You should say, who cares in learning, right? That's not what we care about. We care about generalization. We care about how well it generalizes. Fortunately, we've developed like this mass of tools for analyzing generalization error, right? You know, number of hypotheses in the class that we're working with, growth function, VC dimension, Rademacher complexity. So we can take those tools and apply them here to analyze this algorithm. So I don't have time to go through the details, but you actually have the tools to derive at least one of these bounds. And so I'm asking you to do that on the next problem set. So basically, to analyze the generalization error, what it comes down to is looking at the form of the hypotheses that we're working with. So let's assume that all of the weak hypotheses come from a space capital H, and let's assume that it has some VC dimension D. So if you make that assumption, we can look at the form of this hypothesis H, and we can use one of the bounds that we talked about. One that's particularly useful is the bound in terms of the growth function. And if you work that out, you do the calculations, what we can show is that with high probability, okay, now I'm putting delta in. So with probability at least 1 minus delta, we can show that the generalization error of this combined hypothesis is at most its training error plus, and then the additional term here, okay, so this one we already show is going down quickly, and the additional term is like t times the number of rounds, d, the VC dimension of the weak hypothesis space, plus log 1 over delta, as usual, over m. This softo notation just means we're ignoring log factors, okay? And this should seem like a pretty reasonable bound because D is the complexity of the weak hypotheses that we're working with. And the combined hypothesis is a combination of t of those weak hypotheses. So it makes sense that the complexity term that's appearing here is t times d, right? So the problem, okay, are people okay with this? And again, I'm going to ask you to prove this as an exercise or a problem. The problem with this kind of bound is what kind of behavior does it predict? Well, I mean, it's not necessarily a problem, but just what kind of behavior does it predict? Well, so here we could plot error. Here we can plot number of rounds t. And so we prove this theorem that the training error is going down exponentially quickly. So we expect the training error to go down super fast. But what this bound is saying is that the generalization error should go down at first, but as we keep running boosting for more and more rounds, this term will overwhelm things and we expect it to go up. So in other words, we expect to see overfitting as we've discussed before. That's what this bound predicts. That can happen with boosting. It's possible. Oops. Okay. I won't go through this, but here's an example where it actually does overfit. Okay, it can happen, but there are lots of other typical cases where it does not overfit. So this is another typical case. Okay, this was a cartoon, obviously. Here's an actual run of the algorithm. Again, we have error on the y-axis, number of rounds on the x-axis, but now on a log scale. I could have said this was a log scale too, whatever. It's a cartoon. Okay, the training error. Okay, so here we're using an off-the-shelf learning algorithm called a decision tree that we haven't talked about. It used to be a thing. People still use it. They just don't get excited about it anymore. They're still useful, definitely. If you just use decision trees, the algorithm is called C4.5. It gets about 13% test error. That's this line up here. If you use boosting on top of it, you get a test error of about 3%. So it really can help on problems like this. So what about the learning curve, the shape of how learning evolves as you run the algorithm for more and more rounds? Well, as predicted, the training error does go down very quickly. And after only 5 rounds, the training error is 0 on this problem. What about the test error? So running it on a separate test set. Well, as predicted, the test error does go down, but it just keeps on going down, 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 down. Even after 1,000 rounds, the test error has not started to go up again. And hopefully, if you've taken anything away from this course, this should seem like just impossible. Because after 1,000 rounds, we are talking about this extremely huge and complicated classifier. So each one of these decision trees has about 2,000 nodes, whatever a node is. There's something that make it up that are related to its size. So we're combining 1,000 of them. So we've got this classifier that has like 2 million nodes in it. So it's this huge, extremely complicated classifier, and yet it's performing well. And it should seem especially weird that the test error keeps going down even after the training error is 0. So after 5 rounds, training error is 0, right? After 1,000 rounds, it's also 0. This classifier is 200 times more complicated by any reasonable measure than this one. And yet, its performance is much better than this one. We would definitely expect this smaller, simpler one to be better. So what's going on here? Yeah?
Maybe this is exactly what you're going to say, but what would be driving the propagation of any kind of signal to change the classifier, right? Because I thought you needed...
I see. Yeah, why can you even keep running boosting after the training error is 0? That's a good question. So we're talking about the error of the combined classifier. So the combined classifier has 0 training error, but each one of these weak classifiers continues to have error, I think in this case around, 30%, let's say. which means that you can just keep on running the algorithm. Epsilon t will be like 30%. You can keep updating the distributions. You can keep going. It seems pointless, but it works. Yeah.
Also, I'd like to add a notion of similarity between these weak hypotheses that we are building, so that, like, let's say hypothesis 1, how similar it is to hypothesis 10, and then this number will probably go to 1 at the end. So these are very, after some point, these are very similar.
It's hard to get a handle on that, and if anything, it seems like boosting is deliberately trying to make the weak hypotheses as diverse as possible, because it's deliberately trying to make things hard, and so it's trying to force them to be different.
Like, my point is there should be probably some round, like this T star, where then there is no way to more diverse based on the data set that we gave it initially. So if that's fixed, then there should be some rounds that you can actually.
So maybe it would like start cycling or something. Yeah. Okay. So hopefully you see that there's a puzzle there. Yeah, maybe one more.
The way to get a bound on the VC dimension of big H, which is relation to T and the VC dimension.
Well, then you end up with a bound like this if you do that.
Like the VC dimension of.
Well, it's in terms of the growth function, but you could do it in terms of VC dimension too. Yeah, you could. The VC dimension will be something around TD. Yeah. So it's still giving the wrong result. Yeah.
Can you prune the HTs and effectively reduce the size? Like remove some of them and still have the same?
Maybe. Let's come back to that idea. Okay, so to the question of how many rounds of boosting T, well, if you're in a case like this, it doesn't matter too much. You can just run it a long time. You know, that's kind of what it's saying, if you can do that. But we clearly have a puzzle here. We clearly have a puzzle. So the problem.
Before you answer the puzzle, can you explain why it is 200 times more complicated?
I'm just speaking in intuitive terms. Just because it's 200 times bigger. This one is a combination of 5 decision trees. This is a combination of 1,000 decision trees. So just in gross size, if you were to write it down, it's 200 times bigger.
In terms of the actual code that you need, it's not 1,000 times more. You run out of.
Roughly is, yeah. Okay. Yeah, because you're just listing 1,000 trees versus listing 5 trees. Yeah, just in gross size. It's intuition. It's not. Yeah. Okay. So the problem is that the training error is not telling us the whole story. The training error is not telling the whole story. The training error tells us whether the combined classifier is correct or incorrect on each example. That's all it's telling us. And to understand what's going on here, we also need to think about the confidence of the predictions that are being made by the combined classifier. So the kind of argument that we can make, and that I'll try to sketch for you in the minutes remaining, the kind of argument that we want to make is that, yes, after 5 rounds, the training error is 0, so it seems like nothing is happening. But as we continue running boosting, the predictions on the training set of the combined classifier get more and more confident, and that increase in confidence translates into better generalization performance. So that's the intuition for the argument. Now, to turn that into a mathematical argument, you need a way of measuring confidence. What does confidence mean? How do we define what confidence means? Well, I said that the combined classifier is really a weighted majority vote. So every time a new example X comes in, this combined classifier holds a little election among the weak hypotheses. It doesn't weight them equally. It's kind of like the electoral system in our country. So it holds a little election, right, and gives different weights to each one. Now, in a real election, how do we measure confidence in the outcome? Well, we measure confidence using the margin. It's really the margin, the number of votes that the winner gets or not the number of votes, the fraction of votes that the winner gets minus the fraction of votes that the loser gets. We can use the exact same measure here. We can also use margin to measure confidence. So if we have an example x, y, so in other words, y is the correct label for x, then the margin for this example would be the weighted fraction of correct votes for this. Okay, so let's see. So we add up over all of the weak hypotheses which correctly classify this example. Okay, here are all the ones that are correct of their weight. Okay. Sorry. Before we do that, it's more natural to take a, all right, let me not do it formally. Let me do it in words. Okay, we can take the weighted fraction of the weak hypotheses that are correct minus the weighted fraction that are incorrect. Okay? So if we do that and you work this out, what this means, what this ends up being is just, it actually simplifies, if you do it mathematically, it just simplifies to being y times f of x, where f, little f, just means this with the weights normalized. Okay, so f of x is the same, is what we had before, divided by the sum of the weights so that they're normalized. Okay, so this is the margin. Let's see. So this margin is a number that's always between -1 and +1. It's always between -1 and +1. If you think about it, the sign tells us whether the combined classifier is correct or not. Okay, because if the margin is positive, then that means that y agrees with the sign of f. But the sign of f is just the same as the prediction of the combined classifier. So here's 0. Here's h incorrect. And its magnitude, its absolute value, tells us the confidence. Okay, so confidence near 0 means that the weak hypotheses are almost evenly divided in their predictions on this example. So this would be very low confidence. And here would be high confidence and correct. And here would be, down here would be like high confidence incorrect, right? We all know people like that, right? Okay, so I clearly don't have time to go through an analysis of this. So let me sketch the main idea of what we can show. So once we have a definition of confidence like this, a margin, then we can do an analysis that has two parts. First of all, we can show that this algorithm tends to increase the margins on all of the training examples, given the weak learning assumption, given this assumption over here. Okay, given that assumption, we can show that it tends to push the margins to the right. And the second part of the analysis is to show that if the examples have large margin, then that translates into better generalization performance. And it's possible to prove a bound that's completely independent of t. So the kind of bound we end up with, rather than, it still depends on d, the complexity of the weak hypotheses, but it's completely independent of the number of rounds. So for the first part, again, I'm asking you to do this on one of the problems. By the way, I forgot to say the name of this algorithm. This algorithm is called AdaBoost. So maybe, so for the first part of that analysis, I'm asking you to do it as a problem. For the second part of the analysis, let me just say very quickly how this bound would change. So instead of proving a bound like this, okay, we still are proving a bound on the generalization error. But rather than looking at the training error, we would here have the fraction, I'll just write in words, of training examples with margin below some value, let's say theta. Pick some threshold and say below that theta means small margin, above it means large margin. Okay, so rather than fraction of examples that are misclassified, we look at fraction of examples with small margins. And then this term over here becomes, well, we want to get rid of that t. Okay, so we'll get rid of the t, d. The other stuff stays the same. And then we are going to pay a penalty for how we choose theta, because we expect larger margin means smaller, better generalization. So here you get a bound that's like d over theta squared. Okay, so this is the type of thing that we can prove. If I had one more class, I would have loved to have shown you a proof based on Rademacher complexity. There are actually multiple ways of proving this, but one way is using Rademacher complexity in a somewhat in a very clever way. Let me just show you, and then I really will stop. But let me just, it's not just theory that suggests that margins are what's going on. And I wanted to talk about boosting also because it's kind of a case study of how practical and the theory can go together. And so let me just show you this movie of how the margins, what happens to the margins on this same data set that I've been using as an example. So this is the cumulative distribution of margins, right? And here's the test error. This is after 5 rounds. So it's cumulative distribution. Again, margin is between -1 and +1. Since it's cumulative distribution, that means that most of the examples are where the slope is steepest, like in here and here, but still a significant number of examples with kind of low margins in this region. So as I play this movie, watch what happens to the margins over here and how it relates to the test error. I know, movie and quotes, yeah. Okay, so I'm backing up. So this is after 1 round, and then 2 rounds, and 3. Oops, here's 5 where we started before. And now you can see what's happening. The margins in here are kind of, the examples with margins around in here are kind of getting pushed to the right by this algorithm. And the test error is going down correspondingly. And you can end up getting this convergence to this nice distribution. I don't think we really understand why you get this nice clean distribution like this in a typical case. What we do understand is that it gets pushed to the right, but why it ends up with this nice, beautiful, smooth thing, I don't know. And the test error is going down correspondingly. Okay, I am sorry I went over. You guys have really been a great class. I've really enjoyed this. I hope you have too, and that you enjoy the rest of the summer school. And sorry to cut off questions. Nice to meet all of you.